Today, we have the pleasure of having Dr. Alvin Chua from Caltech to give us a seminar talk. So the title of his talk is Computational and Statistical Techniques for Scientific Analysis in Gravitational Wave Astronomy. So let's welcome him and give his talk.
Yeah, right, thank you. So first of all, I'd like to say thank you as well to Prof. Chan for the opportunity to give this virtual seminar. So my talk today will be on some of the computational and statistical techniques that my collaborators and I have adapted or developed in order to solve scientific analysis problems in the field of gravitational wave astronomy. So this area has become a very active subfield of astronomy since the Nobel Prize winning discovery of gravitational waves from a binary black hole merger, and this was made by the LIGO detectors back in 2015. But as the field matures, there is a growing need to do things better, be it more accurately or more efficiently or both. So this is especially the case if we are to achieve the scientific aims of near future space-based detectors, such as the LISA mission. So that's actually one of my main research interests, and that's an illustration of LISA, the detector in the top corner here. Okay. So in the first part of my talk, I'll give a very light overview of gravitational wave astronomy to introduce the broader setting for most of my work. So I'll start by describing what gravitational waves are, what generates them, and how they interact with matter. I'll then briefly recap the main results from the past 5 years of ground-based observing, which is conducted using interferometric detectors such as LIGO. And then I'll also introduce the space-based detector LISA, which is an European Space Agency mission that will launch in the next decade. So in the second part of my talk, I'll then provide a primer to gravitational wave scientific analysis from a more abstract point of view in order to summarize the essence of the computational and statistical problems that I work on. And finally, I'll describe some of the techniques that I've contributed to the field in recent years, with the general aim being to solve these above problems in a better way or to even solve them at all. Okay, so what are gravitational waves? They are radiative perturbations in the gravitational field, and they are a generic consequence of any theory of gravity with a finite speed of propagation. So in general relativity, gravity is simply the curvature of space-time, and its evolution is governed by the famous Einstein field equations, which are written here. So these equations essentially tell us that objects with mass curve space-time, and simultaneously, the space-time tells the objects how to move. So gravitational waves are generated by accelerating masses, or more precisely, by systems with accelerating mass quadrupole moments. So what this means is that most moving objects will produce them, and it's actually easier to ask what doesn't. So a particle that's moving in a straight line at constant speed will not produce gravitational waves. A perfectly symmetric spinning disk or sphere will not produce them. And a pulsating sphere that expands or contracts radially also will not produce them. So although there are gravitational waves all around us, they interact very weakly with matter, and hence radiation from everyday moving objects is far too weak to be detected because such objects are simply not massive enough. Now, astrophysical objects are massive enough, but most of them are still moving too slowly to generate strong radiation. And as an example, Jupiter going around the sun only emits about 5 kilowatts of gravitational waves. So that's roughly the power output of a large electric heater. And therefore, the generation of gravitational waves that we can detect will require extremely energetic astrophysical objects. So these include neutron stars, black holes, and other compact objects, or core collapse supernovae, or even the rapid expansion of the early universe itself. Now, far away from their source, gravitational waves have a simple description with a particular choice of coordinate system. So they are essentially spatial plane waves with two polarization states, known as the plus and the cross modes. So as such a wave passes through the plane of the screen, the plus mode will cause a ring of points arranged on the screen to oscillate as above, while the cross mode has the same effect but just rotated by 45 degrees. So let's consider the effect of a plus polarized wave on 3 inertial test masses, which are set up in an interferometer-like configuration. So in the standard description, the masses have fixed coordinates, and it's actually the metric of space-time, that is to say the way in which we measure distances, it's that changes differently in the two directions. And hence the light travel time in these two directions also changes differently, and this is a measurable physical effect. Now, it's not necessary to use light to measure this effect, nor is it necessary to have inertial masses. So for example, the masses can be electromagnetically bound particles in a rigid object. So it's easier to see this if we shift to a lab coordinate frame, where the metric is now constant and it's the masses that move instead. So this gives rise to an effective gravitational force that acts on the masses. And in this description, if the masses are inertial, then the distance between them will explicitly change. While if they are bound, then they will be subject to gravitational stresses and strains. And therefore, gravitational waves have very real physical effects. They can transfer energy and angular momentum away from sources, and they interact with matter in a tangible way. However, these effects are tiny, even for the most energetic astrophysical sources. And that's simply because they are so very far away. And by the time their signals actually reach our solar system, they typically have a strain or a relative change in length that is smaller than 10 to the minus 15. So in the 5 years since the first detection of gravitational waves, we are now able to find astrophysical sources fairly consistently and reliably. So here's a brief update on the present status of ground-based observing with interferometric detectors. So there's a current network of 4 ground-based interferometers that's observing in the kilohertz band. So this network comprises the 2 LIGO detectors in the United States, Virgo in Italy, and Kagra in Japan. So together they have detected exactly 50 stellar mass binary mergers to date. So the first observing run of this network was undertaken by just the 2 LIGO detectors. So it resulted in the well-publicized discovery of the binary black hole merger GW150914, as well as 2 other sources. So 150914 was essentially 2 discoveries for the price of 1. So it was not just the first direct detection of gravitational waves, but it also provided the first direct observation of 2 merging black holes. So these plots here will be very familiar if you were following the news in 2016. So they show the actual noisy signal that appeared nearly simultaneously in the 2 LIGO detectors, which are located at both ends of the continental United States. So in the second observing run, a few more black hole mergers were detected. And near the end of the run, LIGO was joined by Virgo. And together, they saw the first neutron star binary merger, GW170817. So this was also the first gravitational wave observation with an electromagnetic counterpart. And indeed, it had several such counterparts because the merger was seen across the spectrum from gamma rays to radio waves. So the gamma ray burst that's sort of depicted in the top plot here, it was picked up just 1.7 seconds after the time of merger, which you can see from the frequency track of the source in the spectrogram of LIGO data below. Now, the third observing run was divided into 2 halves, but the second was cut short by the pandemic just after Kagra started taking data. But nevertheless, this run has contributed nearly 40 of the 50 sources so far. And one notable source was the black hole binary merger GW190521. So that produced the first known black hole in the intermediate mass range of between 100 and 1,000 solar masses. So there was also GW190814. This was a binary merger with the smaller mass falling in the so-called mass gap between neutron stars and black holes. So that it's actually not clear whether it was a heavy neutron star or a light black hole. So all 50 stellar mass mergers from the 3 runs are indicated in the plot here by the vertical curves that join essentially the 2 lighter masses to a heavier one. So all of those sources were at the high frequency end of the gravitational wave spectrum. Now I'll briefly introduce the near future space mission LISA, which will observe at lower frequencies. So LISA stands for the Laser Interferometer Space Antenna. Its design uses 6 inertial masses, which are housed in 3 spacecraft, and these spacecraft are separated by 2.5 million kilometers. So the spacecraft will communicate with one another through laser transponders, and they are drag-free in the sense that they do not apply any forces to the masses along the interferometry axis. So LISA will be placed in orbit around the Sun, trailing 20 degrees behind the Earth, and this animation shows the cartwheeling motion of the LISA constellation as it goes on its orbit. And the mission will be operational for 4 years with the possibility of extension up to 10 years. So LISA is in space because we want to observe the millihertz band of the gravitational wave sky, and that ranges from 0.1 millihertz to 1 hertz. So the number and variety of sources in this frequency band is far greater than in the kilohertz band for ground-based observing. And so there's a lot more astrophysics we can do there. Now, putting a detector in space removes the noise from large-scale changes in Earth's gravitational field, and it also allows longer arms, which give greater sensitivity at low frequencies. Now, the lengths of these arms are not constant, of course, but the data can actually be post-processed to give 3 standard interferometric combinations, which are linearly independent. So 2 of these are essentially the familiar Michelson type interferometers, but with 60 instead of 90-degree arms. And these will be used to measure the 2 gravitational wave polarizations. Now, the third combination is essentially a Sagnac interferometer. So this is a common path configuration, which is largely insensitive to gravitational waves, and it can be used to measure the noise in the data instead. So funding has been approved for the mission. It was selected as the 3rd large class mission in the European Space Agency's Cosmic Vision program, and the scheduled launch date is 2034. However, work has already formally begun, and a prototype design for the instrument and data processing framework is required by 2025. So this is when the mission will actually be formally adopted for the implementation phase. And here I'll briefly mention also the proof of technology mission, LISA Pathfinder. So that concluded in 2017. It was a resounding success. So Pathfinder had 2 initial masses in the same spacecraft, shown here in this picture, and just 40 centimeters apart. So this spacecraft was placed in orbit around the Lagrange point between the Sun and the Earth. And because of this, the much shorter separation between the masses, Pathfinder was not actually sensitive to gravitational waves. But what the mission successfully demonstrated is that the drag-free technology that will be required for LISA is feasible. So this was done by measuring the displacement between the 2 masses to within 0.01 nanometers. And this same precision will be achievable for LISA because it does not depend on the separation between the masses. So impressively, the performance of Pathfinder actually exceeded its own target, and it's already met the mission requirements of LISA itself. So yeah, in this plot here, the red line is the LISA noise requirement, and the blue curve below it is actual Pathfinder noise. Okay, so right. So that was a very brief and quick introduction, and I think that's enough physics for the rest of the day. So now, as promised, I will give a quick primer to the process of scientific analysis in gravitational wave astronomy. So this can essentially be split into 2 closely related parts, solving the forward and the inverse problems. So I'll describe the traditional framework for solving these types of problems, and then I'll explain why there is a strong need for new and improved techniques in this area. So an inverse problem in science is to deduce the causal factors underlying a set of observed data. So given some time series data from a gravitational wave detector, we want to find a map from the data to some physical parameters of interest. So in non-textbook problems, this must typically make use of parametrized forward models, and these models actually map the parameters to the observables in the problem. So in gravitational wave astronomy, both the forward and the inverse problems are quite different from those encountered in most of traditional astronomy. And this is due to 2 distinctive factors. 1, the sources are often highly relativistic, and 2, the data from detectors is often dominated by noise. So as a result, the forward step typically involves the high accuracy modeling of complex dynamical motion, while the inverse step must usually establish the presence of a signal in the first place. So in some sense, then, the theoretical and computational challenges that are presented by these forward and inverse problems are a bit more similar to those in physics, for example, high energy physics experiments. But the comparison is not quite apt either, because in gravitational wave astronomy, we are still dealing with natural events rather than experiments. And the analysis cannot be repeated in order to quantify the statistical errors. Now, the basic example of a forward model in gravitational wave astronomy is that of a waveform model. So that describes the response of the detector to a gravitational wave signal from an astrophysical source. So this will be denoted as a map from the source parameters theta to the gravitational wave signal as seen by the detector, h of theta. So considering the case of a single signal for simplicity, we can write the data as x equals h of theta plus n, where the noise n is described as a realization of a zero mean stochastic process, and is often assumed to be Gaussian and stationary as well. Now, in realistic studies, we often need forward models for the noise as well. That is to say, the noise covariance sigma is parameterized and estimated from the data as well. And that's because it's often not possible to get an independent measurement of the noise. Now, forward models can also be defined for populations of sources that allows observations to directly constrain astronomical laws rather than the properties of a single source. So let's consider the case where the signal is from an astrophysical binary, which is the most common and important type of gravitational wave source. So such a source can be described fully by around 10 to 20 physical parameters, including those that are intrinsic to the binary, such as masses, the spins, and the initial conditions, and also those parameters that are observer dependent, such as the sky location and the distance. Now, the signal has at least two independent channels corresponding to the two gravitational wave polarizations, and these typically comprise between 10 to the 4 and 10 to the 6 samples in time. So the waveform model H can then essentially be viewed as a map from Rs into Rd, with D several orders of magnitude larger than S. Now, approximate closed form expressions for H can be derived for some simpler sources, but in general, we'll need more accurate models that are evaluated by numerically solving Einstein's equations in some form. So these equations are a set of 10 coupled PDEs, and the waveforms themselves are also very large vectors. So the most accurate models that we have are actually too computationally costly to use directly in data analysis. So the standard way around this is to construct models that utilize fits to numerical data for certain waveform quantities. But the difficult part here is to ensure that these models are still accurate enough so as to not bias the scientific analysis. Now, gravitational wave data analysis generally uses waveform models to find solutions to the inverse problem. So we are most interested in two types of solutions. So one is a map from the noisy data X to what is essentially a single bit of information that represents whether a particular signal is absent or present. Now, the other is a map from X to a probability distribution for the source parameters given the data. So the actual processing of the data itself uses standard techniques from signal analysis, such as match filtering, where the signal is extracted from the noise by convolving the data against waveforms. But in a more abstract sense, we can consider this filtering operation as an inner product on the data space that is weighted by the power spectral density of the detector noise. So that noise-weighted inner product for two arbitrary time series in the data space is defined here in terms of their Fourier transforms and the power spectral density Sn. And in this, I've actually abused notation a bit because that integral is actually a sum over D frequency samples. Okay, so these two types of maps essentially describe the two procedures of detection and inference. So strictly speaking, detection is concerned with calculating the statistical significance of any candidate signal that's found in the data. But in practice, a pre-established threshold level of significance is used to decide whether the signal is absent or present. So detection is intrinsically frequentist in nature, and that's because we care about false alarms due to noise. So in other words, a large number of noise realizations, which can be either simulated or measured, they are used to compute the threshold level for some detection statistic at a fixed false alarm rate. So an example of a detection statistics would be the signal to noise ratio, rho, on the right here. And that's just really the inner product between the data and a normalized waveform from a waveform model maximized over all possible waveforms from that model. Now, the other procedure of inference is concerned with obtaining estimates of the source parameters along with their associated errors. So here, instead, a Bayesian treatment is used because there's only one data set. And both the parameter and error estimates are then described by essentially the posterior probability of the parameters given the data, which by Bayes' theorem is equal to the likelihood L times the prior pi, and normalized by the evidence Z. So the prior for the source parameters is ideally obtained from astrophysical theory or observation, but in practice, it's usually chosen to be uninformative or very simple. The likelihood function is the probability of observing the data given the parameters. So it is a defined quantity in this analysis, and it corresponds to the originally assumed setup that the data consists of Gaussian and stationary noise, plus a single signal that's described by H. So both procedures of detection and inference can be computationally costly. And this statement is actually true even if your forward models, even if the waveform models that are used are very fast. And this is because detection is essentially a numerical optimization problem, while inference involves density estimation, which is usually done through Monte Carlo sampling, and that's even more expensive. Okay, so why are new techniques needed for all this? So there are two overarching themes that crop up repeatedly in gravitational wave scientific analysis. So it's the need for accurate calculations and the need for efficient calculations. So the difficulty, of course, is that there will always be a trade-off between the two. And this is depicted in a sort of schematic way by the curve on this diagram. So that represents the best possible set of tools that might be available to us for a particular scientific task. Now, the cross on this diagram then represents the minimum accuracy and efficiency that's required to realistically perform this scientific task. So when applying a new technique to any given task in gravitational wave astronomy, the general goal is then to try and improve the trade-off, either by doing things more accurately at the same efficiency or doing things more efficiently at the same accuracy. So both of these will have a similar effect, which is to expand the area under the curve. Now, there's also the possibility of doing things more cleverly, by which I mean to use the tools in a different way so that they can achieve the original task, but with reduced requirements. And the effect of this is instead to shift the cross down towards the curve. Now, it's true that currently existing techniques are good enough to meet the requirements of ground-based observing. That's why it's been so successful. And it's also fair to say that efficiency is usually not a hard requirement in scientific tasks, especially if one just has to wait a few times longer to get results. However, in scientific analysis for the future space-based detector LISA, the curve and the cross on this diagram are extremely far removed because of various reasons. There are many more overlapping signals in the data. The signals will be much longer and much more complex, and also existing methods will not scale easily. So therefore, the development of new techniques actually becomes necessary in order to achieve the basic aims of the LISA mission. And in short, I would say that this is actually the one slide that would sort of broadly summarizes and describes a large part of my research in gravitational wave astronomy. Okay, so now let's move on to the final part of my talk. Here I'll introduce some of the computational and statistical techniques that I've been working on in the past few years. So I've organized this into three particular topics that might hopefully be of some interest to this audience. Although the actual techniques themselves, generally, they would draw upon combinations of all three. So the first topic is reduced order modeling, where I'll talk about compressed representations for waveform data. The second is deep learning, and here I'll discuss the increasing usage of neural networks for forward and inverse problems in gravitational wave astronomy. Now, the third is information geometry, where I'll describe a somewhat novel manifold-based posterior sampling algorithm that I published as a general statistics paper last year. Okay, so reduced order modeling. So recall from earlier that the waveform model H defines a map from the S-dimensional parameter space into the D-dimensional data space. So we can refer to the image of the map as the signal space, and this is effectively an S-dimensional submanifold of the data space. Now, the aim in reduced order modeling is to represent the signal space as an n-dimensional linear subspace, which is spanned by some reduced spaces B in the data space, and the goal is to make n as small as possible. So the optimal error in representing the signal space by this linear subspace is given by the Kolmogorov n-width, which is defined here. But in words, it is essentially the worst case error of the best possible basis that has size n. So if we want to find a reduced basis that satisfies the n width, it's a computationally difficult optimization problem. So here I'll focus on a more practical alternative, which is to use a greedy algorithm to construct a basis. Now the idea here is to start with an arbitrary waveform as the basis in the first iteration, call it B1, and then to find the most orthogonal waveform to the existing basis at each iteration. So once you have this most orthogonal waveform, then the orthonormal component of that waveform is then added to the basis via your usual Gram-Schmidt. And a regular reduced basis that is constructed through this greedy algorithm is known to nearly satisfy the Kolmogorov n width, in the sense that the decay of the worst case error for the basis actually falls off with n in the same way as the n width. Now, this reduced order modeling approach was first introduced in the context of gravitational wave modeling by Field et al. 10 years ago, and it's gradually becoming a standard technique. So when it's used to compress waveforms, the compression rate, which is actually d over n, the rate that can be achieved is often a factor of around 100 or more, depending on a specific example. So this compression is also virtually lossless because the representation error of the reduced basis is less than machine precision error. So for all practical applications, we can write any waveform in the signal space as equal to its projection onto the reduced basis, and thus purely in terms of its projection coefficients, alpha, as shown in this bottom equation. Right, so the first and the most natural application of reduced order modeling is to leverage this compression when we are fitting a faster surrogate model to a set of accurate numerical waveforms. So the fit can be done at the level of the alpha coefficients as a function of theta, and this is only a vector of length n as opposed to the full waveform h of length d. So in this equation here, I've explicitly restored the physical direction of time. But however, an approach that's more commonly taken is actually to use a method called empirical interpolation to choose a set of n points in time, denoted capital T, and to instead fit the waveform values at those times across parameter space instead. So this works because the waveform can equivalently be written in terms of these waveform values or nodes, as well as some other basis that can be evaluated as shown on the right here. Now, what's the point of this? The motivation for this approach is that the empirical interpolation nodes, they generally vary more smoothly over theta because they're physical in some sense, and therefore they are easier to fit. So here's a diagram that may or may not make things clearer depending on how you like to think about it. Doesn't really help me, to be honest. So the vertical red lines correspond to the original reduced basis, and the red points at the bottom are their associated parameter values. Now the blue points in the physical direction of time are the empirical interpolant nodes. And the horizontal blue lines are then fits for these nodes across parameter space. And finally, if you want to compute the waveform at an arbitrary value of theta, one just has to evaluate the node fits at that value in order to obtain the coefficients of the waveform with respect to the empirical interpolant basis. Okay, so a follow-up application of reduced order modeling in gravitational wave scientific analysis is a method called reduced order quadrature. So that allows faster evaluations of the likelihood function with pre-computed weights. So it relies on the empirical interpolant method because the inner product between data and waveform can essentially be written directly in terms of empirical interpolant nodes. It's given by this equation here. However, the reduced basis must now be constructed in the frequency domain instead. And as a reminder on the right here, so this inner product term is actually, it appears as the cross term in the standard likelihood. And it was defined originally as a dot product between two frequency domain vectors. So the main feature of this reduced order quadrature method is that the sum that's used to evaluate this inner product is now over n instead of d components. And that, of course, leads to computational savings. Right, so more recently, my collaborators at NASA JPL and I proposed the possibility of doing data analysis more natively in the reduced basis domain. So the general idea here is to project the noisy data onto the reduced basis space, and then to perform inference directly with the coefficients of the data and the waveforms without needing to link back to the physical domain. So this projection of the data h plus n onto the reduced basis space can be written as the projected signal alpha plus the projected noise nu. So we call this projected data beta we can show that the original likelihood can then be cast into a reduced form, which is statistically equivalent. So we use the fact that the noise-weighted inner product actually reduces exactly to the standard dot product on the reduced basis space, and we derive the first equality shown here, so there's an extra term gamma, which is the projection of the noise onto the orthogonal complement of the reduced basis space. But this extra noise does not actually depend on theta, and so if we use the term on the right as the likelihood, it does not change the statistical properties of the inference problem. So this term on the right is the reduced form of the likelihood. It also depends only on sums over n rather than d components. And so it provides a conceptually cleaner alternative to reduced order quadrature. And in fact, it's even slightly faster due to the fact that the latter method only handles the cross terms in this square of differences. However, as I mentioned earlier, the reason for using empirical interpolation in the first place is that the fitting of reduced basic coefficients is more difficult, especially for a higher dimensional parameter space. Now, our proposal for getting around this is to use a neural network to fit alpha, which is actually the primary point of that work. I'll elaborate more on that shortly, but first I'll take a few slides to sort of segue into the next topic that I want to talk about, which is deep learning. Okay, so most of you will have heard of deep neural networks for machine learning. And for those who are less familiar with them, maybe let me try to demystify the concept of neural networks a little bit, just in the context of scientific applications and for the purposes of this talk. So one common statement about neural networks is that they are a bit of a black box in the sense that you don't know what's going on inside. So that's partly valid, but I think it's more useful maybe to think of them simply as nonlinear statistical models, which can be used to perform classification and regression tasks, and also to do so in a highly efficient way. So neural networks typically comprise multiple layers of computational nodes called artificial neurons between the input to the network and its output. So when we're performing regression, the general aim is to describe the relationship between variables x and y with a function, call it n. So the neural network is such a function. It depends on x and some weights or network parameters, w, and then it approximates y with some statistical error. Now, training the network then refers simply to optimizing n over the space of weights for some set of training examples. Now, we usually hear terms such as supervised and unsupervised learning, which mean that the training set consists of XY pairs or just X, respectively. And the terms classification and regression mean that the dependent variable Y is either discrete or continuous, respectively. So is it then fair to say that neural networks really are a black box? I would say not totally. It's true that the functional form of N, or in machine learning terms, the architecture of the network, is often very arbitrary and very opaque. But this is not really so different from a phenomenological model that has many degrees of freedom. And essentially what neural networks do is they provide us with a powerful algorithmic method of constructing and training such models. Right, so although neural networks have been around for a while, their usage in gravitational wave astronomy has only started growing really rapidly in the last 3 to 4 years. So I was lucky enough to make some early contributions. Now, neural networks are very versatile models. They have been used for a large variety of applications in gravitational wave astronomy, including low-level tasks for the more technical procedures of detector and noise characterization. But let's focus on the 3 main classes of applications that are most relevant to scientific analysis. So the general idea of using neural networks for signal detection was really what kickstarted the community's interest in using deep learning for this field. So I won't talk too much about this because I haven't done any work in this area personally, but it was first proposed independently by 3 separate groups, and there's been a large amount of follow-up research since. Now, in the area of waveform modeling, my JPL collaborators and I were the first to combine neural networks with reduced order modeling in order to construct fast fits for waveform data. So variants of our method were later applied to model comparable mass binaries for ground-based observing by another group. and also to binaries with an extreme mass ratio by myself and a different group of collaborators. Now, the last application is inference. So our group at JPL and another group at Glasgow University, we use different methods, but we train the neural network so that it can estimate the true Bayesian posterior for the parameters of any detected source. So the most promising thing about such methods is that they can produce the posterior estimates almost instantaneously, whereas standard posterior sampling in gravitational wave inference is usually a procedure that can take hours to days. Now, shortly after our work, the two methods were adapted and combined essentially by a third group to train improved networks that can handle higher dimensional posteriors with multimodal structure. So I'll now elaborate a bit more on our own work in using neural networks as forward and inverse models. So for forward modeling, the task is really just that of straightforward function approximation. So we want to fit the neural network N to a function, say the full waveform H in the general case. And we want to do this by minimizing some distance-like quantity between them over the parameter domain. So this quantity is called loss in the field of machine learning. So for function approximation, the most common loss function is the mean L2 distance, which I've written out explicitly here, where the subscript I is an index over all the examples in a large training set. Now, neural networks are known to be good at function approximation, and in principle, they can deal with high-dimensional problems as well as any other method, although the curse of dimensionality will always be present to some extent. And as I mentioned before, if we want to fit full waveforms in their raw time or frequency domain representation, that's rather impractical because they are so long. So in the work that I described earlier, we take the approach of first compressing the waveform model through reduced order modeling, and then we fit the neural network to the reduced basis coefficients alpha instead. So we tried several different network architectures for this, but in the end, we found that the best results were given by the simplest and oldest type of network called a multi-layer perceptron, or alternatively, a dense or fully connected network. So as a proof of concept, we applied this method to a 4-parameter binary waveform model, and we demonstrated that we can achieve comparable speed and accuracy to the more standard surrogate waveforms described earlier. So this scatter plot that I've shown here, it shows the accuracy of our fit. The yellow points across the parameter space of the model stand for test examples which have good accuracy, and the black points are poorly fitted examples. So in the domain of validity for our fit, which is defined by the red line, the median accuracy is above 99.5%. So there are several nice advantages of our method over the standard surrogate approach. And one of them, one that I mentioned previously, is the ability to do native data analysis in the reduced basis domain. And that's because we are able to fit the alpha coefficients directly instead of the empirical interpolant nodes. Another is the fact that a dense network is built entirely out of simple closed form operations, and hence it emits analytical expressions for its Jacobian and higher derivatives. So these derivatives are obtained for free during the training of the network, and they can be used to compute derivatives of the full waveform, which in turn can be employed in data analysis to calculate things like the Fisher information of the posterior, shown on the right here. However, there are some challenges with the present approach, and the main one is that we generally need high precision in waveform modeling, but I would say that precision is actually the one thing that neural networks are not really designed for. So in our studies, we found diminishing returns with our efforts when trying to get more precision out of our fits. And it seems more like an intrinsic limitation of neural networks rather than any particular thing we can do. So maybe the best approach going forward is to instead alter the problem to suit the tool. And for example, we can do this by not fitting the full waveform, but only parts of it that don't have to be quite so accurate. So this idea was realized in a separate and more recent piece of work where the focus is on constructing waveform models for extreme mass ratio binaries. So as the name implies, these are binaries where one object is much less massive than the other by a factor of 10 to the minus 4 or so. So extreme mass ratio binaries will be important sources for the LISA space detector. And the modeling and the analysis of these binaries is very challenging because these are sources with very complex orbits, as depicted in the diagram here. So that leads to a lot of structure in their waveforms, as shown below. However, one factor in our advantage is that the long-term evolution of extreme mass ratio binaries is also very slow compared to the orbital timescale. And so this allows us to cast the waveform in a more optimal form for modeling. So essentially what we do is we perform a decomposition of the gravitational wave field into harmonics of both its angular dependence as well as the three fundamental frequencies in the orbital motion. So this allows us essentially just to write it as a sum of many harmonic modes, like so, where each mode is described very simply as a wave with slowly evolving amplitude and frequency. So the long-term evolution of the amplitude and the phase depends on the source parameters through a smaller number of smooth trajectories, call it G, as a function of time. So modeling G to the required accuracy is actually the gist of the whole problem. It's theoretically difficult and it's done through other methods, which I won't go into here. But once the theory is completed, there are fast methods for actually computing these trajectories. So the phasing is also straightforward to obtain once G is on hand. So the only remaining task then is to compute the large number of instantaneous mode amplitudes in a suitable way. So what we need is essentially a map from any instantaneous value of G to the vector of corresponding mode amplitudes. Now, the good thing with this description is that the amplitudes don't need to be quite so precise because correct phasing is far more important for gravitational wave data analysis. On the other hand, there can be thousands to even hundreds of thousands of mode amplitudes to compute. So for the first model we considered, which is the simpler special case of a larger mass, which is non-spinning, the number of modes is already around 4,000. So as you can guess, what we did is to apply reduced order modeling and the neural network fit to this problem. So we first compressed the vectorized amplitudes in the direction of the harmonic index, rather than in the physical direction of time and or frequency, as was done before. So this reduces the size of the fitting problem by around 40, and it can then be handled fairly easily by a neural network to decent accuracy. So this plot here is a visual comparison of the worst case waveform in our model against the corresponding waveform from a more accurate reference model. So there are actually two waveforms shown there, but as you can see, the differences are barely distinguishable. And furthermore, our method is a few orders of magnitude faster. So this framework is thus promising for achieving both the speed and accuracy requirements of future LISA signs. Okay, so now I'll move on to our other application of neural networks in gravitational wave scientific analysis, which is to solve the inverse problem of inference. So here, the general idea is to treat the task of posterior estimation as regression by fitting a neural network to some representation of the posterior. So this is done by minimizing some statistical distance between the network's posterior estimate and the true family of posteriors for some training set of data realizations. So the Caltech-Leibler divergence is best used for this because it leads to the very simple loss function shown on the second line here. And here the summand is precisely the KL divergence between the direct delta function centered at parameter value I and the network posterior estimate for the data realization I. Now, if the network estimate is represented via coarse-graining as a histogram instead, then the loss simplifies further to the expression on the third line. And this expression appears more commonly in machine learning as the standard cross-entropy loss for classification problems. Now, this approach of treating posterior estimation as regression is known as a likelihood-free method because it does not require the definition of a likelihood. It only requires access to a generative model for the data. So this generative model is often simulated, but it can also be nature itself, although that's not really applicable in the gravitational wave context. So in our work, we again work natively in the reduced basis domain to lessen the computational difficulty, but the method is actually more general in principle. And we showed that it's feasible to train different types of neural networks to instantly output parameter posteriors given some noisy gravitational wave data. So these posteriors can be represented either parametrically, such as in the form of a Gaussian mixture model, or as histograms. So this plot here shows an example of two-dimensional marginalized posterior estimates from our method for 5 different signals. So we use the Gaussian mixture representation in this example. So the red points are the true signal locations in the mass parameters, while the black lines are the true posterior contours. The yellow regions are then the posteriors, which are estimated by our neural network. And you can already see by eye that these are a good match to the true posteriors. So the method can also resolve multimodality in the posteriors, although we only managed to achieve this with the histogram representation. So these are one-dimensional marginal posterior estimates for 3 different signals, which have multimodal posteriors. And again, the yellow regions are the estimated posteriors, and the black lines are the true posterior density functions. So our method has several interesting potential applications. For example, it could be used to instantly generate rough posterior estimates for the sky position of a detected source, and so as to enable rapid follow-up observations by electromagnetic telescopes. Now, the estimates could also be used as proposal kernels within Markov chain Monte Carlo algorithms for a more thorough recovery of the posterior. And this is because it's well known that MCMC has optimal convergence when the proposal density is the same as the target density that's being sampled. So there are, however, some limitations to the current version of the method. So the simple parametric models that we use are unable to resolve finer structure in the posterior, while histograms are able to, but clearly histograms will not scale well to high dimensional problems. So a more recent method seems to cope well with both of these issues by making use of what are called normalizing flows. So these are just invertible maps between a simple probability distribution and a more complex one. So this is the next area that we are interested in exploring and developing. Now, finally, the last topic that I'll talk about today is information geometry. So strictly speaking, I think this term refers to the study of statistical manifolds. That is to say, the topic deals with Riemannian manifolds, where each point is a probability distribution. And this is essentially the case for the family of posteriors, which was considered in the previous part of the talk. However, I want to use the term more loosely here to include any applications of differential geometry to probability and statistics. So this is because in the gravitational wave context, the signal space of the waveform model itself is also a Riemannian manifold, as I mentioned earlier. And the Bayesian likelihood and posterior are then probability distributions defined on this manifold. And so the question is, can we use any of this in a more practical sense to help us to solve the inverse problem of inference? So here I'll introduce a new method for manifold-based posterior sampling that I recently developed. So this, I would say it's best described as a general computational statistics algorithm for sampling efficiently from manifold-restricted Gaussian distributions. So here's the setup of the problem. So we want to sample from a target distribution with a density of the given form P of theta. So in this expression, we assume that alpha is a smooth embedding of the S-dimensional manifold, capital theta, into D-dimensional Euclidean space. So capital theta is essentially the parameter space, which is equipped with the pullback of the Euclidean metric. Now, equivalently, we can also think of this distribution as a standard D-dimensional Gaussian distribution, but with variables that are constrained to lie on the image of alpha. So note that I'm using alpha here to denote the map, which is the same symbol that's used for reduced basis coefficients in the earlier part of the talk. But the reason for this will become apparent, and there shouldn't be any confusion anyway. So this restricted Gaussian form for the density is actually quite general because it can be used to describe any set of observables with assumed Gaussian noise. And this is very common in science. So one example is, of course, the standard gravitational wave likelihood I introduced earlier, but after applying a whitening transform W. But the end goal is actually Bayesian inference. So what we would really like is to sample according to P times an arbitrary prior density. So I won't go into details here, but in the manuscript associated with this method, I describe several ways to do this for common priors, such as uniform on a hypercube, or Gaussian priors, or even fully generic priors, although that's more just in principle. Now, in a nutshell, the method, I would say, can be described as performing importance sampling on the tangent bundle of the manifold. which is naturally included in the Ombion Euclidean space. So we start off with a set of n samples, theta I, that are distributed according to p. So we have to assume that we can obtain these through other means, such as a standard sampling algorithm. Now we also require the mapped points, alpha I, which lie on the image manifold, and they are already computed in the process of obtaining theta I. And finally, we require the Jacobian, ji, which forms a basis for the tangent space at each point. So the Hessian, hi, contains information about the normal curvature of the manifold at each point, and it can be incorporated quite naturally into the method, but it's not strictly required. And this is because in practice, Hessians are expensive to compute, so we want to avoid using them. Now for each point in this base chain, we generate m additional points, beta ij, in the Ombion space. So these lie off the manifold, as shown here in this diagram. So they are drawn from a Gaussian kernel with mean alpha I and some covariance, which is defined by a scalar quantity C at that point. So Ci is the compactness, I call it C for compactness, of the generated points around alpha I. It can depend on the Hessian, the Jacobian, or neither. But what it is parameterized globally by a single parameter epsilon, and that's effectively the only tuning parameter in this algorithm. So for each of the m times n beta ij, we then pull them back onto parameter space via a projection onto the corresponding tangent space. So these projected points, beta ij perp in red, and the pullback points, theta ij, are given by these expressions, which depend on ji and its pseudo-inverse ji plus. Now these pullback points, theta ij, are not distributed according to the target density p. So they must be assigned some appropriate importance weights before they can be treated as samples. So the conditional density q prime of theta ij, given theta I, is exactly Gaussian, but in order to define the weights w, we require the marginal density q, which, as seen in the denominator here, is effectively the convolution of q prime and p on the manifold. So this is generally intractable, but because p is locally Gaussian, we can compute linearized weights that have a Gaussian functional form. So the final output of this algorithm is a set of m times n weighted samples, and crucially, this is obtained from just n evaluations of the map alpha and its derivatives. Okay, so I am running a bit short of time, so I don't know how much time there is for questions. Maybe I'll skip this slide. Okay, so here is the method that's applied to several examples which are presented in the manuscript. So first is a Gaussian that's restricted to a parabola in the plane. So that gives the target density, which is indicated by this blue curve in the bottom plot. So that's the target density. So there are just 200 points in this base chain, indicated by the blue points in the top plot, the blue dots. So each of these is then used to seed 500 Ombion points. So you end up with 10 to the 5 points. These are indicated by the red dots. And after projection and pullback, a histogram of the weighted samples is actually a good match to the target density, even if you use a very small bin width. So another example is a Gaussian that's restricted to a family of variable size Klein bottles, which is embedded into R5. So the parameter space here is 3-dimensional, and the 1- and 2-dimensional projections of the posterior are shown in this plot here. So, okay, it's a bit confusing, this plot, but the orange curves above the diagonal, they show the posterior contours for the method if we use just a base chain, a very short base chain of just 200 points. And the red curves below the diagonal are for a base chain with a slightly longer one with 2000 points. But both of these chains are upsampled to 10 to the 5 points using the method. And it can be seen that their contours are actually a good approximation to the blue curves, which are for a full-length reference chain with the same number of points. So naturally, if the base chain is longer, as it is for the red curves, then the method performs better. Now, finally, let's look at a more real-world application that ties back into the rest of this talk. So here, the manifold we consider is a 2-dimensional submodel of the same binary waveform model that was presented in the forward modeling work introduced earlier. So reduced order modeling and deep learning are used to compress the on-beyond dimensionality of this 2D model from 10 to the 4 physical samples to just 173 reduced basis coefficients. So as I mentioned before, a neural network also comes with reliable analytical derivatives. So that makes this model actually quite well suited for a demonstration of the sampling method. So again, the gravitational wave posterior can be cast in the required form for the target density, and we can use the method to draw samples from it efficiently. So in this figure here, we place the true parameters in the center of each plot. So if we look at the top left plot, it's a high resolution histogram of the base chain with only 1,000 samples. It's clearly under-resolved. You can't really tell anything from it. The top right plot is a histogram of the upsampled base chain using the method. And the plot below it in blue is for a reference chain with the same number of samples for comparison. So you can see that the posterior obtained from this method is a good approximation to the reference posterior, and the computational gains in this example are actually about an order of magnitude. Okay, so I think I'm out of time, so I'll just leave my summary up. Yeah, thank you for your time.
Okay, so, are there any questions for Dr. Chua?
So you mentioned that currently the efficiency and accuracy of the computational methods are by far not enough to evaluate the data that are expected to come from this LISA mission. During the last few years, has there been substantial progress? So saying today, are we much nearer to get sufficiently strong methods?
Right. So that statement that is not current methods are not good enough is actually valid as of now. So just to clarify. So right now, so put it another way, if the mission launches tomorrow, we would not be able to actually achieve the scientific objectives of the mission. So yeah, so basically there is a need for these techniques to be developed. And even though it's like 10 years away, that's actually probably not a lot of time.
I mean, in the last few years, did people already get closer, or is the progress in the last few years already significant?
It's been gradual, I would say. And actually a big part of that is sociological. So the mission was actually originally a joint mission between NASA and the European Space Agency. But about 10 years ago, NASA actually pulled the funding for their mission for budgetary reasons. And then it was only after the success of LIGO that they came back into it. So as a result, there was this huge gap in activity by the community. So that, yeah, basically the progress was stalled on all these topics. So right now it's picking up again because LISA is now a real funded mission. But I think that there's still a lot of work to be done before we can catch up.
So of course, there is also an area of manifold learning, so quite popular, I think, in the last 10 years. So how is your work related to this?
Right, yeah. So I was actually trying to, when I was writing up that paper on the last topic, I was trying to draw parallels with manifold learning, but actually it's quite a different problem, because the problem that I'm dealing with is for a defined probability distribution, which I'm just trying to draw samples from. Whereas manifold learning is really, you're trying to actually learn structure from data. So in some sense, perhaps it's more closely related to the second topic, which I talked about, which was to basically do posterior estimation with neural networks. But yeah, then again, not quite. So I would say, yeah, manifold learning is related in the sense that the techniques are similar. They both use geometry. But yeah, I would say I can't see the connection right now.
So I'm also interested in some more general questions, if you don't mind. So, so for this gravitational waves, so of course, the one direction is simply to be able to detect them, but is there also the hope to solve some very important problems using this? So once people are able to better detect them, so is there some larger goal behind this?
Yeah, so so the original goal, I would say, is more from a fundamental physics point of view. So we wanted to essentially try and prove one of the last remaining predictions of general relativity. So after this was done, now the field has actually shifted quite significantly just to astrophysics, right? And that's just because the only sources that we have are astrophysical in nature. So basically, currently, what gravitational waves can do is they just provide us with a different way of doing astronomy, basically to observe these sources in different ways, and also maybe to observe sources that we can't even see using regular telescopes. But in the future, as you pointed out, as the precision, as our ability to do science and to measure these sources improves, and as we get more of them, eventually, I think we will be able to do science that relates to more back to fundamental physics, right? So you can imagine if we can observe a source very precisely, we can extract its orbital dynamics very accurately. We could use these as tests of relativity, and also even more speculative, we could even probe into the quantum gravity regime. You know, if the precision of our measurements really gets really good enough. But so I think all this actually depends very strongly on the success of the space mission LISA, because right now, if we just use these ground-based detectors, there's no way that they are intrinsically limited in terms of how precise they can be. So we really need the space mission in order to open up the possibilities.
So you mentioned that even the changes in the gravitational field of the Earth causes serious measurement errors. So actually, are these errors larger than the errors caused larger than the gravitational waves themselves?
Yes, I would say so. So we can sort of think of it as like noise, right? So if you have changes in the Earth's gravitational field, so these come in at around the 1 hertz sort of area. So we're actually limited by that. So if you look at, so basically signals will currently they are actually already drowned out by noise. So the only way we can extract them is using these sort of electrical engineering techniques like match filtering to extract them. So they're already drowned out by noise, but we can still do it because we observe them for enough cycles. But eventually, you know, as you get down to lower frequencies, the noise just becomes too great. So there's we can no longer do that, and that's as you pointed out, is a part of the inherent limitation faced by ground-based observing.
So one last question. So this so when they detected these gravitational waves, they traced it back to certain phenomena like a merger of neutron stars. Actually, is this really sure that this is the source of this, or is there some uncertainty?
Right. Okay. So the first detection, I would say it was groundbreaking. It was accepted by a large part of the community, although there were skeptics, because ultimately, you know, it's just a single detector. It is claiming an observation. It's not corroborated by any other independent experiments or detectors. So that was the first discovery was for just 2 black holes, right? So you can't see this merger through any other means. But the neutron star binary, which occurred in 2017, that was really sort of quite a clear stamp that, you know, we are actually seeing these things and they are astrophysical in nature. And that's because, as I mentioned, we actually saw the same source in all the other different electromagnetic channels. So I think that actually has put to rest any final lingering doubts that you know these might be caused by things that are not astrophysical in nature.
Thank you. So I don't have further questions.
Thanks. Great questions.
Are there any questions from others? Okay, otherwise, in the interest of time, I think let's just thank the speaker. Thanks, Dr. Chua, for the interesting talk.
Thank you. I hope it was interesting to the audience.
Thank you very much.
Thank you.